to reiterate once again, just if you have any questions, so that you don't forget, just note them down, and we'll go through all of them at the end. And our last but not least presenter of this session, we have Zain from Rutgers University, and the title of the research project is Constraining the Formation, Time and Depth of Magnetic Sources Within the Martian Crust. And I'd just like to invite Zain up here to present research.
Awesome, just make sure that works right. All right, I'll get started now. So, hi everyone. First, I want to say thanks to the previous speakers. Those are amazing presentations. Thanks to the conference organizers, and thanks to you guys, the audience. I'm sure a lot of you traveled really far. You guys have been a great audience so far. I'm looking forward to getting to know you guys over the course of next week. If you ever see me, feel free to come and ask questions. I'm happy to talk. But we'll get into it. So, my name is Zain. I come from northeastern United States, university called Rutgers University. And yeah, we'll get right into my work. So my work, still in space, but a bit closer home, is on good old red planet Mars. So some more basic information. It's the fourth planet from the sun, closest to Earth, and probably, as humanity, we know the most about Mars as compared to any other, or at least relative to Earth, or world center. But anyways, what you probably know more about Mars from is the sheer amount of media that's out there. So we have movies, we have games, old newspapers, books, shows, all this stuff, going back decades and decades in the past. And one of the most common themes across all these media is that Mars is a really, really harsh place. The atmosphere is so thin that anything that relies on oxygen, it can't live. During winter, it gets so cold that anything that relies on water is just going to freeze to death. And also, not to mention, it's being constantly bombarded by solar radiation, which is essentially a concentrated cancer beam, and it'll break apart DNA and any types of organic molecules, atom from atom. And so this makes it so that water, or liquid water, which is one of the most essential biomarkers of life, is essentially going to be non-existent on the surface of Mars. So, end of story. Mars is inhabitable in the past or future. But that's not quite the full story, because as scientists have been collecting more and more data on the surface of Mars, we've been finding some confusing little quirks that make it seem like the past of Mars is hiding more information than it lets on. So some of those might be, we see these massive polar ice caps of CO2 ice, possibly housing thousands of cubic meters of water, or water ice, and we don't know how it got there, what's underneath the surface. If we look at actually topography or the lay of the land, we see these kind of like river channels or outcrops. That might indicate some erosion due to possibly liquid water flowing at some point. If we get high resolution images, we see these valley networks that have hydrated minerals and clays that could only existed if there was flowing water there at some time. And once we got these more high resolution pictures from the Curiosity rover, we could see, if we compare these to Earth, we're seeing these types of mineral formations that are only present on places on Earth where there's high rushing water rates. More recently, we discovered these things called recurrent slope lineae, RSLs, which are during the hottest, warmest seasons on Mars. We get this salty water that flows on the surface, actual liquid water on the surface of Mars. It's not long-lived, but it's there, liquid water on the surface of Mars. And last December, we recorded the first live asteroid impact on a planet other than Earth, and this was on Mars. And if you look closely around like the white area around there, Christmas crater, you see this white stuff. We think that that's ice that got deposited from underneath the crust, and sure enough, after a couple of days, it disappeared. Likely it melted. So what this is telling us is that there was water ice underneath the surface of Mars, and it got excavated out. And so all of this is just saying that Mars probably just didn't have water. It had a lot of water sometime in the past. And this could be like these little oceans or lakes or basins, all the way over to these large surface bodies of water, almost like oceans, that could have covered the entire planet. And these are some artist renditions. It could have been this picture of like Mars that could have been Earth-like sometime far, far in the past. And so all of this is to say that roughly 4 billion years ago, much like my heart, Mars is probably rich, warm, full of life, but then, much like my heart, presently is cold, sterile, and dead. And so the natural question is going to be, what caused such a drastic change over time? What actually happened on Mars that led to this change? And so the answer is going to lie at the core of Mars. And so here's this diagram, and when it's complicated, I'll simplify it. We start with the inner core of Mars, or not of Mars, any planet in general. This could be Earth, Mars, a sun, any large celestial body. So the inner core is going to be extremely hot, and it's going to have a lot of pressure. On the outside, the heat dissipates a bit, and so you're going to have this molten level, this molten lava that's much like a lava lamp. It's heating and it's rising, and it's cooling and it's sinking back down. That goes in a cycle through some electromagnetic processes. This is going to induce this large-scale planetary magnetic field. Now, it might be complicated. A simplified way to think of this is just going to act like a big old bar magnet. And so this is called a planetary dynamo. This is dynamo theory more specifically. And so actually, Earth has an active dynamo. That's why we have compasses. That's why they work, because each compass has a little magnet inside it and then aligns with the dynamo of the planet. But dynamos have more importance beyond just making our compasses work. See, the sun emits this stuff called solar wind, which is these highly energetic charged particles, literally moving at millions of miles per hour, and these are highly corrosive to life. But Earth, because of its dynamo, the magnetic field interacts with the solar wind and deflects it, protecting us on Earth. And so, as you might have inferred, Earth has a dynamo. Mars right now does not have a dynamo. That's why the solar wind can eat away at the surface and destroy it. And so, going back to this question of, what happened to Mars that caused such a drastic change, we likely think that it is because of the death of the dynamo. And you might think, okay, cool, nice theory, nice story, but do we have any evidence that actually shows this? And, yes, we do. So if we kind of look at a timeline of Mars, on the axis, these are the different eras, geological units of Mars. On the right, we have the most recent. All the way on the left, we have millions of years back, so that's 4.5 billion years ago. What we think is that we first got confirmation that Mars does not have an actively present dynamo, no magnetic field, in the Mariner 4 flyby around 1964. However, it's really cool. Around 1984, we found this meteorite in Alaska. What we figured out is that this likely came from Mars 4 billion years ago and landed on Earth. If we look at the magnetic signature around that, we can actually tell Mars likely had an active dynamo 4 billion years ago. That's plus or minus about 1 billion years, very big uncertainty bars. But what we know for sure is that Mars used to have an Earth-like dynamo, but now it doesn't. And so since then, we've, refined our cross-magnetic field measurements using 2 orbiters, MGS and MAVEN, and 1 lander, InSight, which has given us a much better map of the crustal magnetism of Mars. And it's important that's the crust because it's the outermost layer, almost like a pizza crust of a planet, that we're measuring the magnetic field. I'll get more on that in a minute. So there's been a lot of work kind of analyzing, obviously, I hope I've convinced you that the dynamo of the planet is very important to the past and present habitability and a bunch of geological processes in there. So a lot of work has gone into modeling the dynamo cessation, figure out when that ended, using plate tectonics, hydrothermalism, magnetic intrusions, volcanism, you name it. Now my approach is going to be a bit different. It is going to be through the lens of impact craters, asteroid craters on the surface of Mars. And the euphemism I like to say is almost like a snapshot of the dynamo at certain times. Let me explain that more. So imagine, let's cartoon example, imagine this molten layer of crust, so hot lava. It could be from a volcano or something, but it means it's hot, and those arrows represent the magnetization up there. So right now it's all over the place, very weak, not really magnetized to be a random rock you find outside. But under the influence of an external field, i.e. the dynamo, the rock is actually going to get this thermal remnant magnetization. It's going to align itself with that dynamo, and then this makes it so when it cools, it'll effectively be set in stone, such that if the dynamo weakens or changes direction, the cross magnetization is going to remain just like that. And so fast forward a couple however long until a specific impact event, and this is where that comes in. If we pause at the moment of impact, we're going to get these intense heating and shockwave pressures that are going to, almost like when the crust formed, it's going to demagnetize the crust. But important, remember, it is again susceptible to background field. So if there is a background field, this is where that snapshot analogy comes in. It's going to almost like record what the field is at that time. And so it's really cool. It's going to cool, or the crater's going to form, it's going to cool. But we got a record at the time of formation what the dynamo was. Craters are like a telescope into the past to let us see what was the dynamo like, however many billion years in the past. And so again, this is a cool theory, but do we actually have data to back this up? At the top, you have a map of Mars topology, lay of the land. At the bottom, you have crustal magnetization. And in the circles, I have the major impact basins of Mars, the biggest craters on Mars that are a couple of thousand kilometers in diameter. And you see that around them, there's no real magnetic field signature. So this shows that at least in the biggest examples, we do observe this demagnetization going on in the crust. And so this kind of brings us to work. So a lot of work is done before about this idea of impact-induced demagnetization and using that to time when the dynamo turned off of Mars. Problem is, it's not the best work. So the magnetic models used were old, not as high quality. They're only looking at 4 or 5 craters, the biggest ones, and some of their techniques aren't as advanced as are possible now. So the results of this is, again, if we have the periods of Mars at the top, some of the geological activity, these are the estimates of when the dynamo turned off. It's all over the place, from 3.5 billion years ago to 4.7 billion years ago. Very large error bars all over the place, not agreeing very well. And so the idea is that the way that I'm trying to improve on this is, one, we're going to have these high resolution magnetic field models. We're going to do a comprehensive search of all candidate craters, trying to do 855 craters that we're going to search for these signs of impact-induced demagnetization. And we're going to use these more high-resolution crater dating techniques to find out exactly when in the past these craters formed. And so here's an example of what that analysis might look like for one sample crater. So this crater is named Henry Crater. I didn't choose that name. And so start with that magnetic field data. So the satellite we're getting our data from is the MAVEN satellite. It has a magnetometer aboard it. And what that data will kind of look like after some complicated processing is we have these tracks. What each of these lines represent is the magnetic field data from MAVEN as it went over this thing. So you have multiple times kind of MAVEN went over this as it went around and around on Mars. And what you see, key, right in the middle, so red means it's strongly magnetized, blue means it's demagnetized. If you look, as it goes over the crater, it's demagnetized. This is the impact-induced demagnetization that we were looking for, which indicates that at the time of formation, Henry Crater the dynamo was likely off. We can do some more analysis, some stuff about Fourier decomposition. What really matters is the central plot in the middle, which tells us the overall strength of the magnetic field or crust magnetization around Henry Crater. You could rotate it, put it on top, and you kind of see that it lines up. It's very strong on the sides, but it dips in the middle. Demagnetization. And so this is one of our strongest examples actually of demagnetization, nearly 80% reduction in the field. And so we kind of repeat this process for all 855 craters. We assign this arbitrary rating, just strong demagnetization like that example I showed before would be a -3, 0 would be, nothing's really going on here, 3 would be the opposite. So the crust inside the crater is more magnetized than the surrounding area. And so now that we have our magnetization ratings for our craters, we want to move on to finding out when it formed. And this is some more complicated stuff. It's using the subcrater density, so how many craters came after Henry Crater, and using some complicated techniques, we could pretty much figure out with high resolution that Henry Crater roughly formed 3.6 billion years ago. Again, we repeat this for all of our craters on Mars, and we end up, although our sample size reduced from 855 to just 17, we are very confident in the results that we're getting from these few craters. And then if we plot the age versus the magnetization of these craters, notice an overall downward trend, which makes sense. Early on, the dynamo was very strong. Later on, the dynamo weakened a fair bit. But what we kind of key things to look at right here, we get this demarcation here, and what that kind of represents in terms of the past thing. 3 main conclusions. So first is that the dynamo was likely active about 4 billion years ago for a bit. The key thing is that it turned off for a bit, possibly reverse directions, and then it turned back on again about 3.9 billion years ago, and it turned off for sure about 3.6 billion. And to date, this is our highest resolution, this is our best understanding of when the dynamo of Mars was actually active, and this allows us to refine other things and draw some more conclusions about crustal formation mechanisms. That's the work so far. That's most of my work. That's the thing I could put a neat little bow around and go on. But as is the case with research, as I'm sure all of you know, is that you think you answered one question, 100 more come up. So, the kind of toy example I showed before about impact-induced demagnetization. In theory, this looks very nice. We saw this example of Henry Crater, which was exactly what we wanted to show. Something I kind of left out is that we only see these nice examples in 10% of cases. And what's even weirder than that is that if we count this continuum of crater diameters, smallest ones are 0. You have a couple of, the biggest ones are about like 2,000 kilometers. We expect this line 300 kilometers. Anything bigger than that should be demagnetized like Henry Crater. Anything smaller, you're not really getting enough energy delivered to the crust to demagnetize it to the right extent. However, if you look at Henry Crater, our strongest example of impact-induced demagnetization is 167 kilometers big. It should not be demagnetized like it is now. Even more, there are more examples like that. And a lot of the craters bigger than 300 kilometers, there's no appreciable demagnetization there either. So, what's going on? And so there's a lot of, like I said before, this is an ongoing research topic, but we're starting to nail this down a bit, looking at revisiting our approach. So one idea is that you have the region of impact-induced demagnetization. The other main source is going to be this thing called Curie depths, where inside the crust of a planet, you have these radioactive elements like uranium, thorium, potassium, and as they decay, they're going to release energy, they're going to release heat. So as you go deeper and deeper in the planet, it's going to get hotter and hotter until you get to the point where it gets so hot that minerals just can't retain their magnetization. And so this is a more complicated analysis. Basically, the idea is that if we're going to find impact-induced demagnetization, it's going to be about here. So we do, this comes from more complicated stuff about elemental abundance maps. I'll kind of skip through this, but we get this idea of, this is about how deep it is into the crust before you get to the point where no magnetization could exist. Kind of skip over this, but what we're really aiming for is this type of map. And this is the depth at which we think the magnetic layer of Mars is. what we found out before is that the magnetic layer is kind of buried. It's not exactly on the surface, because you could hit it, but we're not really getting, you could hit the crust, but we're not getting at the magnetic layer. It's probably buried a little bit underneath. And this is how deep we think it is. This is a model from Gong and Wezer, another paper. I'll show a QR code at the end where you can find a specific paper. But this has a bunch of implications for early crust formation mechanisms, a lot of stuff about heat flow and thermal evolution of the planet. But the key takeaways that we give here, thinking about the future. So Mars, very likely hot water, and so it's our best candidate for finding extraterrestrial life that could revolutionize our understanding of biology. Impact-induced magnetization could tell us that our best model to date is that the dynamo likely ceased about 3.6 billion years ago, but there are still some puzzles about crust formation mechanisms. And I'll kind of give my conjecture, my hopeful little thinking. Some examples like Henry Crater, where we think, okay, magnetic layer should be down here, and it should be untouched because the impact didn't have enough layer to get there, or it didn't have enough energy to demagnetize that part of the crust. However, there's water there, which might be possible. There's aquifers, there's magmatic intrusions, there's heat, water. That's all that you need to make life. And so for future Mars missions, hopefully if the data pans out, we should go here and we should drill. That's my kind of conjecture. If we go there, we have the best possibility of finding not just past, but possibly present life on Mars. So that's all. Thank you guys for listening. Scan the QR code if you want more info, but again, thank you all for listening, and yeah, for questions now.
So much, Zane. Big thank you to all our presenters. Now we're just going to open up the floor to Q&A. So if options